5, we've now gone 120 miles. What's my average speed? Remember, mean means average, right? Mean means average. What's my average speed? Well, what's my total distance that I've gone? Between hours 1 and 5, what's my average speed? So how far have I traveled between these 2 hours? 90 miles? How many hours did it take me to do that? 4 hours, right? So all we're doing there is we're drawing a right triangle. We're trying to find the rise over run. We're trying to find the slope of the secant line, right? This is your rise is what, 90, and your run is, wait, did we say 5? It's 4, right? 4, right? And so the average speed would be 90 over 4. What, miles per hour? That's just the slope of the line connecting those two, isn't it? The mean value theorem says what? That there's a point somewhere. This is a huge thing, all right? We know our average speed, right? We know our average speed. The mean value theorem says that it says guaranteed there's some point in this trip that what? You're going your average speed. At that instant, you had to be going your average speed. That's a big deal. If your average speed is 90 divided by 4, that means that at some point in your trip, you had to be going 90 over 4. Let's make this a little easier. Let's do, what? Let's make it 110. That makes that 80. That makes that, what, 20? For better, so I can say it easier. So if your average speed is 20 miles per hour, the mean value theorem says that guaranteed somewhere in your trip, you had to be going 20 miles an hour. It's impossible to not attain your average speed on a trip, unless you can somehow teleport across time and space and reappear, but then it wouldn't be a continuous function. Does that make sense? So as long as it's continuous, you must achieve your average speed. So average, mean value theorem. Okay? All right.
Why do we need to know what the average speed is?
Why do you need to know what it is?
Yes.
Well, the average speed is something that we can get without any calculus, right? The calculus gives us the speed at an instant. That's what we've been more interested in, right? But the mean value theorem says that no matter what function you're ever looking at, somewhere in there you must attain your average value. Whatever the average value of the function is over that interval, you must achieve that in your derivative as well. All right, so I have a question for you. Have I done the race car problem? I don't think I have. No? All right, this is a thinking exercise. I want you to think about it. I'm going to put the problem up here. I want you to think about it and talk to each other. I'm going to give you a few minutes, and then everyone's going to vote and give me an answer. All right? So this is a theoretical problem. All right? There's no way that we could actually do this in reality. It'd be impossible. But we're going to do a race. Okay, this is the start line of a race. We have 2 cars. We're going to have car A right here. That's the top view of car A. Let's make car A red. It's a Lamborghini. Ferrari? Ferrari. Car A, right? And then we're going to have car B, and that's going to be in blue. Hey, B for blue. All right. And they're going to have a race. Okay, here's the race. Here's the finish line. There's the finish line. Yeah,
Looks like 54.
That's weird, right? So start and finish. And here's all I'm going to tell you about the race, is that we started the race, right? They were both on the start line. The race started, boom, they took off. I'm not going to tell you anything about anything that happened during the race. All I'm going to say is at the very end of the race, it was a tie. I mean, a perfect tie. That's why this is theoretical. It would be impossible for us to ever measure whether or not it would be a perfect tie, because we don't have instruments precise enough to measure things like that. So it's theoretical. All right? Understand? They start together, boom, 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 whatever happens, they tie. Yes? So here's the question. I have two questions for you, and I want you to think about this. Think about it deeply. First question. Is there a speed which both cars must travel? And when I say a speed, I mean an instantaneous speed. Is there some speed which both cars must travel, or both cars must attain that speed? First question. Second question is, and these are, yeah, I'll just put it here. If you think so, if so, do they have to travel that speed at the same instant in time? Question. All right, I want to clarify before I let you, because I'm going to step out and let you all talk about this for a few minutes. I want to make sure you understand the question. So two cars start together, they tie at the end. So the first question is saying, is there some speed, let's just say for the sake of getting a speed, 50 miles an hour. Like, is there some speed, 50 miles an hour, that both cars had to at some point, like, attain?
At the same time?
No, just is there some speed that they both have to see? And I should be clear, this is not at the beginning of the race and at the end of the race. This is in between. Both these questions are somewhere in between the race. Is there some speed that both of them must achieve? All right, that's the first question. And then the second question is, if you think there is, then do you think it happens at the same moment in time for both of them? So it's like, let's just take the first question. If I'm car A, is there some speed, let's say 50 miles an hour, that I'm going to see? Guaranteed I have to see it. And then for car B, are they going to have to see that 50 miles an hour also? That's the first question. And then the second question is, if you think that we're both going to see some speed, is it going to happen at the same exact moment in time for both of us? So think about it. You understand? Any questions on it? No? You confused about it? Do you understand it? We're going to vote, and then your final grade will be determined if you're right or wrong. So no. So I want you to think about this, because I'm going to hopefully at the end of this get you to buy into an idea. All right? So.
Can I gamble for his?
All right, you going to think about it? I'm going to go get a drink. Don't look so enthused. All right, does anybody want to volunteer their opinion? Okay, what do you think for the first one?
Yes.
You do believe that they're both going to have some speed. Do you want to kind of justify that in any way? Or you?
Considering the mean value theorem, if at some point, since they started and ended at the same point, they're going to have some common speed.
Yeah, so I think what you're saying is that they, like this graph, if you were to look at it, let's go ahead and graph it so I can help support what you're saying.
Their overall speed is going to be the same, so at some point they must have both reached a common speed.
Their average speed, right? So they both start, let's say this is time, let's say they both start at time 0, right? Yes? And let's say they both end at time, I don't know, let's just call it t, okay? Just to make it easy. That's where they ended. Well, whatever happened in their paths, the red one, the red car, right, started, this is distance. So it starts and it ends at some point, right? And that travels a certain distance, right? Whatever that is, who cares? I didn't tell you how long the track was. And the blue car does the exact same thing. The blue car starts here, right? The red car started here. They both started here. And they both ended together, right? So their average speed is the slope of the line connecting those 2 points, right? So they both have the same average speed. That's what you're saying, right? Both these cars have to have the same average speed because they both went the same distance over the same amount of time. And the mean value theorem then says that for car A, there's some point in here that the tangent line, which would represent the speed of the car at that instant, must be parallel to that secant line. And then for car B, we have the same thing, right? That it has a graph and somewhere in there it's got some point, right? So I like that. I agree. Anybody disagree or want clarification? Was everyone a yes on number 1?
Yes.
Okay, how about number 2? Is it the same point in time for both? No? Is this a strong no? I mean, how do y'all feel? No yeses? There's usually just like one yes just because like you wouldn't be asking the question, right? Or something like that. You think it's yes? Anyone else want to say yes? Do you have any justification for it or any reasoning for it, or just it feels like maybe?
But it's not like it was there. I got a little reasoning, but I don't know how to explain it.
Don't know how to explain it. Okay. So pretty strong no's from everyone. Okay, it actually is yes. All right. There's not only do they both have to go their average speed, they both have to achieve that average speed at the same point in time. And that is counterintuitive. That goes against what your mind is wanting you to believe, right? Right? Y'all said no, right? And normally in a class, someone will say yes, a couple of people will say yes, and they'll try and explain why, and then the people who say no will say, no, that can't be right, and they'll argue about it because it's just like you're going off your instinct, right? And there's no easy way to explain what, like what the reality is, right? It's, like I said, counterintuitive. So would you like to see how you can prove that they actually have to go the same speed at the same time? Would you like to see that? Because what it demonstrates, and this is like the final takeaway of this, is that this is why we have mathematics. It's because this happens a lot in a lot of different fields. If you go off your gut, if you go off your instinct, you can be wrong. And so the math is there to settle it, right? It's like if you're building no, I shouldn't talk about that, but, right? You're building something, you're like, yeah, that should be good enough, You're trusting your instinct. You're trusting, well, you can't. You have to trust the math, right? So this is a good example of a problem that is counterintuitive and very difficult to prove without some mathematical proof, all right? So you all ready? This is really for my like real deep critical thinkers and like math major type people, because this is the way you would prove something like this, all right? So you ready? I'm going to try and prove this. And the way I prove it, you probably would never think of doing this, which is why I want to show you. It gives you some glimpse into the way that like math people have to think, all right? So let me first state what I'm going to try and convince you of. And then you're going to either say like, yeah, if you can show me that, I'll be happy, all right? So a couple of pictures first. Let's go with that picture we just had. Let's call this 0, and let's call this B so we can match the mean value theorem a little better. Car A, I said, started here and traveled, did something, right, and ended here. I didn't draw the graph earlier, but now I'm going to draw it, all right? And just to make that kind of simple, let's call that A of x instead of f of x. Do you all agree that that's a continuous function on a closed interval? Yeah? All right, now I'm going to draw the blue car. Started somewhere, ended somewhere, and I don't even know what the graph looks like, right? I'm going to call that B of x. So I have two graphs, right? Here's what I want to show you. And you'll have to tell me whether or not you agree with this as being enough. I want to show normally in math we write just WTS for that. I want to show there exists a C in the interval 0b such that A prime of C equals B prime of C. Would that be enough if I could show that to you? What am I saying? I'm going to try and show you that there exists a C somewhere in here. I don't know where it is. There's a C somewhere in here that the derivative of that A function at that value C is equal to the derivative of the B function at that value C, which means they have parallel tangent lines, which means the speeds are the same, right? So would you be convinced if I could show you this?
Yeah.
Yes? Everyone? Okay, I'm going to show that to you now, all right? I'm going to prove to you that that's true. All right, I need a couple of things to get this started. I'll be done before we finish up here. So recall just a few things that I'll need. If f is continuous and g is continuous, then f plus g is continuous. This is something we established with the theorem at the beginning when we were talking about continuity. We said, hey, if you have two continuous functions and you add them together, it still stays continuous. And it also works for subtraction. If you subtract two, it's still continuous. So is that all right with y'all? Okay. That's the first thing. Hold on, there was something else that... I think this is nothing you're going to argue with me about. That if you have two functions and you add them together or subtract them and you take their derivative, that you can do them separately, right? Like we've been doing that for a long time. If it's addition and subtraction, you can do those, right? So we're all okay with that? All right, I'm going to need that. So now how in the world do I go show you that there's a C in there that makes this true? So this is the big thing, all right, that is hard for people to come up with. What I'm going to do is define a new function, all right? I'm going to come up with a new function. I'm going to call it, I don't know, M. Capital M of x. And all this capital M function is this. It's the A function minus the B function. So all I'm doing is I'm taking the difference of the two. You can look at it as I'm creating a new function that measures the distance between the two, all right? And now what I'd like to ask you is this. What is M of 0? So what happens if I plug 0 into that function? I get 0 here and 0 here, right? So you get A of 0 minus B of 0, right? And what's that? 0, why? Because they both start at the same point, right? So this is saying, what's the distance between the two cars in the beginning? 0, right? Okay, now I'm going to ask you, what's M of B? 0. B, right? That's the end, right? At the end of the race. What's the difference between their positions at the end? 0, right? Yes? So I'd now like to graph that function m for you. All right? I'm going to graph m. Kind of. Here's what it would look like. Here's what I can say. At 0, where is it? Okay, and at b, where is it? Okay, is this a continuous function? Is m a continuous function? Yes, why? Because a and b are continuous, so the difference of two continuous functions is still continuous, right? So I have a continuous function that connects this point to this point, and I have to draw it without picking up my pen, right? So I don't really care what it looks like, I have to do that, right? Now, what does Rolle's theorem tell us? Rolle's theorem says that, what does Rolle's theorem tell me? Okay, I'm going to write it down. So by Rolle's theorem now, Rolle's theorem, there exists a C in the interval 0b, somewhere in there, such that what's true? The derivative of what function? What function is this graphed? This is m, right? This is m of x. Such that the derivative of m at what value? C must be equal to the slope of the line connecting these 2 points, which is 0. Isn't it just 0 because it's flat? Yeah? I'm like a step away. Yes? You know what to do now? What are you going to do? What's the left side?
It's ax minus bx.
Yeah, if you want to take derivative of m, right, then you're just going to do derivative of each of these separately, right? So the derivative of m at c would be the derivative of a at c, what? Minus the derivative of b at c, but that has to be 0. And now just move this to the other side, and I'm done. The derivative at a at c is equal to the derivative at b at c. Now, did I find the actual value? No, but I know it exists. I'm done. That's kind of crazy, right? I mean, after you see it play out, it's maybe not so bad, but coming up with this idea is not natural, right? So this shows that if two cars start at the same time, and at the same time, straight line, right, straight line race, that there's some point in the race, same point in time, that they look down and they both see their average speed, and it happens at the exact same moment. Counterintuitive, right?
How is this not testable? I feel like you could get pretty close.
What do you mean testable?
Like you said that this is a hypothetical situation. You can't
Well, how could you ever prove to me that they tied?
I mean, you could get pretty close, I would say.
That's why I'm saying how close, because then people could argue that you're not close enough, right? I mean, it's like even with like modern day Olympic races, right? The swimmers, right? Their clocks that measure their times only go to certain precision, right? Like hundredths of a second or thousandths of a second,
Yeah,
right?
Like if they hit the same speed within a fraction of a second, like I feel like that's pretty good.
Well, but to be pure about it, like that's an infinite amount of time to some people, is that little gap. All right, well, let me see. It's 4:12. Let's start getting into the next section. I know y'all are tired and everything else and all that good stuff, but you had a whole weekend and we only have a couple of classes left. So the homework for this will be short, very short. There's only like maybe 2 or 3 problems for Rolle's theorem. All you're doing is verifying, mean value theorem. All you're doing is verifying the mean value theorem. Oh, shoot, man. Huh? I'm debating if we are going to the next section. Yeah, we're going to the next section. I want to talk about one more thing, but we just don't have time. All right. So I told you that the main 2 ideas of figuring out the peaks and valleys of a function were closed interval method and open interval method, right? Closed interval, we've got that. We did that earlier. We're done. Now we're going to lead ourselves into the open interval method, but not directly. We've got to get a lot of things established first. So now what we're going to talk about is how the derivative impacts the shape of a graph. So we have more definitions here. So we have this idea of increasing, decreasing, and constant functions. So when you think of when we look at functions, right, if you're looking at a graph of a function, we would read it left to right like we would read a book, right? Left to right. When we say that a function is increasing, that means it's going up, as you're looking at it, right? It's going up. That's increasing. Decreasing means it's coming down. Constant means it's flat, right? Well, if your function is going up, then do you agree that the derivative at the points that it's going up should be positive? Yes. The slope of your tangent line should be positive at the points. If your function's going up, then the derivative should be positive. And then if your function goes down, the derivative should be negative. And then if you're flat, constant, your derivative should be what? 0. And that's what this first note is about. And I can show it to you. This is an example of a function that's increasing, right? As you read this from left to right, if you were on this like a roller coaster, you're going up, right? And notice that at every point on this function, no matter where we are, the slope of the tangent line is what? Positive. The slope of the tangent line is positive. So here I have the computer measuring the slope. See, those are all positive numbers? And the function is increasing as we move from left to right. On a function like this, as we move from left to right, we're decreasing, and notice the value of the derivative there, right? The derivative is negative at all those points, and so our function goes down. And then, constant, as we move from left to right, the derivative is always what? 0, right? Flat. Yeah, the function's the same number, but the derivative is 0. So that's a very valuable thing to us, because that means that the derivative tells us when a function goes up and down. Like if we take the derivative and we look at that function, if we analyze it deeply, it can tell us when a function goes up and down. And what if I told you that a function went up and then came down? What did you just find? If it went up and then came back down, what did you just find? A maximum, right? What if it goes down and comes back up? Now you've found a minimum. You see what I'm saying? So somehow the derivative being positive and negative is going to help us determine where this function's going and having these hills, peaks, and valleys, right? Now here's a function that does a bunch of different things. So I'm going to move from left to right. Just notice the slope of the tangent line is going to change colors here. Green, right, because we're going up. We get to the top. What? Derivative is 0. Now what's going to happen? Decrease, derivative is negative, and then 0, then positive, right?
So kind of like
It's changing. It's changing, right? We see a change in the derivative. It goes from positive to negative, then back to positive. So now we get what's called the first derivative test. All right, it says here, let's say that you're looking at a function and you've got a critical number. Remember what the critical numbers are, right? That's where your derivative is 0 or doesn't exist. Let's say you're looking at a critical number. So you got this critical number, and then to the left of that critical number, your derivative changes from positive to negative. So here's your critical number, imagine here, and then to the left of that, your derivative is positive, and the right of it, your derivative is negative. Then you've just found a local max, right? Or if you're at a critical number and it changes from negative to positive, now you've found a local minimum. And if it doesn't change, then you have not found either a local max or min. So if it goes from positive to positive or negative to negative, then you don't have a change. You don't have a change in sign, you don't have a local max or min. All right? So this is look at this one right here. Positive derivative, right? We have a critical number up here. That's a critical number. Boom, changes from positive to negative, and look right there, we have a local max. Now, what happens here? Negative derivative, right? And now, what happens there? What's my derivative there? 0. But, so, to the left, this is a critical number, yes? Yes. But to the left of it, what's the derivative? Negative. What's the derivative to the right? Negative. Does it change signs? No, so I'm not going to have a local max or min there. And then, negative, negative. Now, another critical number. Boom, right there. Oh, I missed it. No, you see it's there, right? It goes from negative to positive, and so we should have a local min. Positive derivative go up, negative derivative go down. Okay. So let's do an example here. If f of x equals x to the fourth minus 4x cubed plus 1, find